I'm Karthik. Today I want to talk about our project, realigning language to visual objects with an agentic workflow, presented by me. The challenges are real and hallucinations. Language-based object detection aims to align visual objects with language expressions, while vision language models help scale training data by generating human-like expressions. They often suffer from hallucinations. These hallucinations leads to inaccurate object descriptions, example name, color, shape, deteriorating visual language, element quality. This is especially problematic for small objects or when text prompts are unspecific. For example, if you see what is there in the red box, it says something like the object is a blue and red head run by angle, but it's actually flag. So this is hallucinations get by the model. So we get to our workflow for our real LOD, which is the starting is the raw expressions. The process starts with raw expressions. These are the original unprocessed descriptions or instructions that relate to an image. Second is an image with then detected objects. Alongside the raw expressions, we also have an image that brings process for object detection. This means the system has already identified and labeled objects in the image like person, car or tree. There is a real LOD system processing loop. Inside the real LOD box is a core reasoning and processing cycle. The first part is the planning. The system figures out which steps are needed to align the raw expressions with the detected objects. This is like drafting a strategy. First confirm the detected objects, then match them with the expressions. Second is the tool use. The system uses different tools for object detection algorithms, natural language processes to carry out the planned steps. This could mean checking image coordinates, refining object categories, or passing sentence structure. The third is the reflection. After using tools, the system reflects on the output, asking it to match everything correctly. Is an ambiguity. If something seems off, it suggests its approach before looping back. The looping, planning, tool using reflex. This repeats multiple times until the system feels confident about the alignment. Output is a real and expressions. Once the real and loops finishes, you get real and expressions with the refined description that now accurately corresponds to the object in the image. This means the text is now tightly linked to the image actual contents. The man is standing next to a red sedan in the left part of the image. Take an example for the man is standing in the red sedan. In short, this workflow takes rough descriptions and an image processing through a reasoning cycle, planning, tools and reflection, three steps, and outputs polished, accurate descriptions that match the detected objects. Now we complete our workflow. If we go to a example for our explore, if we see horse, we give the expression like if the is a horse work like standing on a dirt or sand. It processes the three steps planning, tool use, and the reflection and gives us output like the horse is standing on the dirt. This is a refined example. Real-day defines language object data pairs through cyclic process of planning, tools, and reflection. This iterative approach ensures expressions accurately match visual objects. The workflow adapts visual content and text forms, reducing modal hallucinations and strengthening language object connections. Efficient impact, super relative performance. Our Real-LOD workflow constructs a dataset, real data containing 0.18 m million images with 1.4 m real and language object paired data, training a prevalent LOD model. With this data significantly suppresses the existing methods. What the key findings in this? Remote outperforms existing LOD methods by 50% on the standard benchmarks. Data quality is as crucial as the quantity for superior results. A method preserves data quality while scaling up the data quantity. If you see that inaccurate alignment between language descriptions and visual objects in language-based object detection systems cause visual language models sometimes generate incorrect descriptions due to hallucinations. Example, misidentifying object category, color, location, relation, surroundings. Impact. These inaccuracies degrade the quality of the training datasets, leading to weaker detection accuracy. If you see the business consequences, autonomous driving, misaligned descriptions can cause misaligned detections or wrong object identification. In security surveillance, incorrect descriptions could mislead the threat detection. In e-commerce visual search, wrong object detection reduces user satisfaction. The sales conversion. If you come to the enhancements, we can do improved data quality and diversity, expand high quality alignment datasets beyond the current 0.18 million images while maintaining strict filtering for alignment accuracy, include more diverse object types and contexts. Human in the loop validation for difficult and ambiguous cases to reduce hallucinations. We can also enhance prompt and image adaptation, refine the object cropping strategies, smaller crops for the fine details, context-aware extended crops for relational understanding, use multi-turn adaptive prompting so VLMs iteratively focus on the unresolved details, boost agent reasoning, upgrade the state classification logic so the resolution detects subtle misalignment faster, introduce multi-modeling reasoning, train on hard negative examples. We can also use multi-VLM and LLM collaboration. Use assemble VLM for conscious checking. If outputs disagree, trigger the further refinement. We can also leverage self-improvement cycles, extend the reflective step with additional evaluation metrics, example visual learning scores, attribute accuracy. Allow cross-sampling learning. Feedback from one different expressions improves other with a similar context. Cross-domain and multilingual expansion. Apply Real-LOD to other domains where element is critical. Introduce multilingual object rotations to expand applicability or across dataset advancements. This is a conclusion. Key takeaways: multimodal reasoning. Integrate multimodal reasoning to further reduce hallucinations in descriptions. Feedback loops. Incorporate user feedback mechanism for improvement of data quality. This is a conclusion. Thank you.